Okay, so next we see differentiability on an interval and one-sided derivatives. A function y equal to f of x is said to be differentiable on an open interval a comma b if it has a derivative at each point of a comma b, i.e. if f prime of x exists for all x in a comma b. But what about closed intervals? F is said to be differentiable on a closed interval a comma b if it is differentiable on its interior, which is this open interval a comma b. We know that for a closed interval a comma b, this is the interval's interior, and these are the boundary points, which are also known as the interval's endpoints. So, if the function is differentiable on the interior in this sense, and the following one-sided limits exist. One of them is, okay, these limits will be just like ordinary derivative. The only difference is that unlike ordinary derivatives, which are normal limits, this will be one-sided limits. The limit of f of a plus h minus f of a divided by h as h approaches 0 from the right side, and another similar one, but this time f of b plus h minus f of b divided by h as h approaches 0 from the left side. Note that we considered this one-sided limit only because we only have the function defined for real numbers at a and at real numbers greater than a. So that's why h needs to be positive here. Similarly, we only have the function defined for values of the independent variable which are equal to b and less than b. So here we have to take h negative, and that's why we have one-sided limits at the boundary points, the end points. If these limits exist, then we say, besides having all the derivatives at these interior points. If additionally these two limits also exist, then we say that our function is differentiable on the closed interval. Now note that these are one-sided limits. Accordingly, they are not simply called derivatives but one-sided derivatives. More specifically, this is called the right derivative at A and this is called the left derivative at B, because we are considering these one-sided limits. This is a right hand limit and this is a left hand limit, that's why. In fact, we can space here the above limits are called the right hand derivative of f at A and the left hand derivative of f at B. Now here's the thing, we had to consider only these one-sided derivatives because of the nature of these points. They are endpoints of an interval, so f is not defined to the left of A or to the right of B. However, we can also do this for interior points as well. Just like, because after all these are limits now. So just like we can consider the right hand limit and the left hand limit of a function at a point. So such things can also be done for derivatives. The right hand and left hand derivatives of a function can be considered at any point in the function's domain. And these one-sided derivatives are related to normal derivatives in exactly the same way that one-sided limits are related to two-sided limits. These one-sided derivatives and ordinary means two-sided. Derivatives are related in the usual manner. So what is that relation? That relation is this theorem 5 from section 1.4, which we have already seen. By theorem 5 section 1.4, a function has a derivative at an interior point of its domain if and only if its one-sided derivatives at that point also exist and are equal. We need to consider interior points because otherwise if we consider those endpoints, then you may not be able to even talk about one of the one-sided derivatives. If and only if it's one-sided derivatives at this point exist and are equal. So instead of trying to find the derivative of a function at an interior point directly, if you are somewhat skeptical about whether the derivative even exists or not, you can instead try to find the one-sided derivatives at that point and see if they are equal, or in fact even before seeing that they are equal, whether they exist or not. Okay, if they both exist and are equal, then the ordinary derivative also exists and has value equal to that common value. Otherwise it does not exist. So let us next see an example of this. Example 5. So this is our usual function, which is the absolute value function. The function y equal to absolute value of x is differentiable at, well, not at, but I want to say on an interval, on the set of all negative real numbers, and also on the set of all positive real numbers, which one can verify. Okay, but this is not differentiable at x equal to 0. Let us show this by showing that the one-sided derivatives at 0 both exist but have different values. To the right of the origin, and by origin of course the authors mean x equal to 0. To the right of the origin, all our x values are positive. So we have this. Oh, why am I putting x here? Let me first write the difference quotient here. 0 plus h minus the function value at 0 divided by h as h approaches 0 from the right side. So what is this? This is the right hand derivative of our function at the point 0. Now if we calculate this, we are going to get this. H is approaching 0 but from the right side, that means H is positive, and that's why the numerator in this ratio is going to be just H. Okay, and because H is non-zero, this is nothing but 1. So the right hand derivative is constantly 1. Well, I should not perhaps say constantly 1. It is 1 because we are considering it at 0. If you change this point 0 and take any positive real number, there also it will be 1. That's what I wanted to say when I said constantly 1. However, we won't have the same value to the left of the origin. To the left of the origin means here we are going to consider the left hand derivative of the function at 0. Now H is approaching 0 from the left of 0. That means H is negative. And that is why here the numerator is going to be minus H. And we get minus 1. So the left hand derivative is minus 1. Because these two values are different, so the limit of this ratio does not exist as H approaches 0. Not from right or left, it just approaches 0. That limit does not exist. And that is why the derivative also does not exist at 0. If you draw the graph of this function, you can see why. By now we already know very well what the derivative represents. Geometrically, it represents the slope of the graph at the point where you are finding the derivative. So not being geometrically accurate, I am just simply showing how the graph looks roughly. So this is our graph. This is the y-axis. This is the positive y-axis, positive x-axis, the origin. And this is the graph. These lines extend without any end. Now, if you arbitrarily choose any point to the right of 0, that means any positive real number, say x1. At that point x1, or more specifically at this point, which is whose coordinates are x1, x1. Okay. There is a tangent to the graph at this point, which is this line itself, and the slope of that line is 1, which you see here at 0 also. At 0, however, that is not the derivative of this function, but the right hand derivative. Whereas, if you take something else, say y1, to the left of 0, some point, then the corresponding point on the graph is y1, minus y1. Keep in mind here y1 is negative. This, however, is positive. So we have to take minus y1 here. Now the point here is that at this point also, there is a tangent to the graph which is this line itself, and that line has slope -1, which we also see here, and that is also the left hand derivative at 0, and that is why you see that there is no tangent, no unique tangent at the point 0 to the graph. I mean, it seems like the x-axis is also a tangent, something else like this, a little slant line which passes through this 0 also should be tangent, but we know that none of them is a tangent, and the derivative also does not exist at 0. So you can see geometrically, if you have a sharp corner like this, then the function fails to be differentiable at that point, and that is true. But that is not the only situation in which geometrically derivative does not exist. There are other situations as well, and we are next going to talk about just that. When does a function not have a derivative at a point we know how to figure out whether a function has a derivative or not geometrically. A function y equal to f of x has a derivative at a point x equal to x naught if the slopes, here we are talking about the situation geometrically which has come from our study of tangents. So remember how we figured out when tangents exist and what is a tangent in fact. In defining that, we used this thing, and from there only we are actually getting the notion of derivatives. So a function y equal to fx has a derivative at a point x equal to x naught, of course in its domain, that need not be mentioned, if the slopes of the secant lines through the point P, whose coordinates are x naught comma f of x naught, and a nearby point Q on the graph of the function. So what have I written? A function has a derivative at a point x naught if the slopes of the secant lines through P and a nearby point Q on the graph of the function approaches the limiting value as Q approaches P, while all the time being on the graph, of course. If the graph, so basically what we are saying is this. This is suppose your point P and this is the graph of the function. A portion of the graph maybe, and this is your point Q. So what you do, you draw the secant line passing through P and Q, and you keep P fixed but you change Q. You make it move towards P while all the time being on the graph. So the secant line also changes in the limiting position as Q approaches P. These secant lines all have their slopes. So those slope values should approach some limiting value, some real number. If they do, then we say that the function f is differentiable at the point, well, not at the point P, but at this point. And that that limiting value to which the slopes of these secant lines approach, that is defined as the slope of the tangent to this curve at P, or in other words, the slope of the curve itself at P. And that is in fact also the value of the derivative of the function at x naught. If, however, this value does not exist, then the function is not differentiable at x naught and no tangent also exists at the point P. Well, there is one case where also derivative doesn't exist but the tangent exists, namely when the tangent is vertical. In that case, the slope is infinity or minus infinity depending on the situation. That, however, is not a real number. So we are going to say these things. Okay, so basically this is what differentiability means geometrically. And now, when this fails, when the secant lines fail to take up a limiting position as Q approaches P, or become vertical. Say the secant lines, say the graph is somewhat like this. Then if your P lies here, then as you move your Q towards P, gradually the secants assume a vertical position. In that case, the slope will tend to infinity or minus infinity, depending on how the secant lines originally, what type of slopes they had. In this case, the slope will approach minus infinity because all these lines have negative slopes. But if the lines were like this, and then from that position they were becoming vertical gradually, then the slopes will approach plus infinity. So that can also happen. Geometrically, the secants gradually become vertical. Then also the derivative doesn't exist. Then the derivative at x naught doesn't exist. Okay, now besides this, a function whose graph is smooth otherwise can still fail to be differentiable at a point in these following situations. Whose graph is otherwise smooth fails to have a derivative at a point if number 1, the point is a corner so this situation is like that absolute value function graph. It had a corner at the point x equal to 0 and we saw that the function failed to have a derivative there. Geometrically, there is no tangent at that point. Where the one-sided derivatives, that is the left hand derivative and right hand derivative, have different values. And a geometric illustration of this case is also given in the text. So we are going to somewhat carefully draw a diagram showing this case. Say the graph of our function looks like this. Okay, so at this point, whatever this point is, you can, for the sake of seeing what is going on, let us just imagine the x-axis here somewhere and the y-axis is also there. There is no need to draw the y-axis. So this is our point x0, this point. And that is the point P. Let me write P somewhat above this so that we can draw those lines. Okay, so this is actually the point P. Now we have to consider a nearby point Q on the graph itself. That we can consider either to the right of P or to the left of P. So we are going to consider both of them. Say we consider this point Q to the right of P. In order to emphasize that this point lies to the right of P, we put a plus sign here as well, Q plus. Now we draw that secant line. Okay, so this line will be like this. The line is of course a geometric line, so it's not just from this point to this point, it extends indefinitely on either side. And then what you do, you slowly move the point Q, let me not write anything here, towards P, being on the curve itself. So the secant changes, and as you take Q closer and closer to P, I'm again and again writing Q, the secant keeps on changing its position. In the limiting case, the secant is going to assume this position. Let me show that by a dashed line. Okay, when we consider q to the right of p on the graph and then move q towards p, always being on the graph, the corresponding secant moves like this, and when q approaches p, the secant lines should approach this line, alright, and the slope of this line is the right hand derivative of our function at the point p. On the other hand, if I choose my point q to the left of p and denote it by q minus, here also I can join this new q with p, obtaining this line, and then I gradually move this q towards p, changing the secant also in the process. Yeah, it's a bit off. Okay, you can understand what I am trying to do, but messed up a little bit. So let me take another point. In the limiting case, when q approaches p in this manner, the secant lines will approach this line instead. This line, not that line. And the slope of this line is equal to the left hand derivative of our function at the point p. These slopes are different. So if there is a corner like this, the graph is not broken at p, it is joined, it is in one piece, but there is a sharp corner at p. It's as if the graph was originally smooth, but someone pinched the graph at p and then moved it so that there is a bend like that, okay, a bend. So in this situation also, the derivative won't exist. This is one of the cases. Number 2, the point is the cusp where the secant slopes approach infinity from one side of t and approach minus infinity from the other side. Now, what is this situation? In this case, none of the one-sided derivatives exists. One of them is plus infinity, the other is minus infinity. And geometrically, now the graph will look like this. Okay, and for our convenience, here also, let me just show the x-axis. So this is our point x0, and that is the point P. This also looks like a corner, but the situation is somewhat different here. Note that in all these situations, f is defined at x0. x0 is a point in the domain of f, so there is nothing wrong with having a value of the function at x0. We have a value. Here we have a value, here also we have a value. Having derivative, however, is something different than having simply a value. Here, if we run that process, similarly, say this is my q negative, then the first secant from this position is going to be like this. Okay. Then I move my point q closer to P, and the secant moves. So if I keep doing this, eventually what happens is that the secants are becoming more and more vertical. Well, they are not, but they are going towards the vertical line that passes through P. And this of course is going to pass through X as well. Note that all these lines have positive slope. And as you move Q towards P, the slope is increasing. The lines are getting steeper and steeper. And in doing that, they approach, the slopes approach plus infinity. And so, the left-hand derivative of our function at x naught approaches plus infinity. Whereas, if we run the process for points to the right of P, the exact opposite thing is going to happen. So, in this case, the secants all will have originally negative slopes. Oh, and why are they having negative slopes? Because they are making obtuse angles with the positive direction of the x-axis, whereas these secants are all making acute angles. That angle is increasing as you are changing the situation, but all of them here have positive slopes, and these secants on the other hand are all going to have negative slopes. But even having negative slopes, the absolute values of those slopes are increasing. And here also, in the limiting position, they tend towards infinity but minus infinity. So this is the situation where such a point is called a cusp. There is another situation. Oh, and note that in this case, going back to the section where we studied tangents, when this happens, we do not say that the graph has a tangent at that point. If you have a vertical tangent which has slope infinity or minus infinity, then it has to happen from both sides. Either the slope is plus infinity from both sides or the slope is minus infinity from both sides. That is not the case here. That's why we do not say that the graph has a vertical tangent. We say that the point is a cusp. The vertical tangent case is the next case. The graph has a vertical tangent at the point where the slopes of all the secant lines either approach plus infinity or all approach minus infinity. While you make Q move towards P from either side of P. And this vertical tangent case can be illustrated geometrically like this, where only one of these cases has been discussed. You can imagine the other case. Say the graph of our function looks like this. I messed up. This is the problem. I have to do it somewhat quickly. Okay, that's good enough. So here what is happening is that, although it doesn't look vertical, now let me just try once more. It doesn't really look vertical. Okay, fine. So this is my point P. I better not write P here, let me write it here. And again, for convenience, we are going to draw our x-axis so that we can locate the point x0, x0. Let me first take a point Q to the left of P. So that will lie here, Q negative. So now our secant is going like this. Let me extend this line. Okay, I will say why I am extending it afterwards. Let us first see what happens to these secants. As we move our point Q closer and closer to P, and the limiting position is this vertical line that passes through P and also passes through x0. Note that if you started your process from the right side of P, there also you would have considered points like this, and through them, if you consider secant lines also passing through P, then which are nothing else but these lines only. That's why I extended these lines. And all these secant lines have negative slopes. And as you move Q towards P, either from this side or from that side, that negative slope is increasing in the sense that it's increasing in absolute value. So it's becoming more and more and more negative. And all the derivatives approach, what the hell am I saying? All the secant slopes are approaching minus infinity. And here we have really a vertical tangent to the graph at the point P. But minus infinity is not a derivative value because it's not a real number. And that is why in this case also the function fails to be differentiable at P, although in spite of not being differentiable at P, the graph does have a tangent, and that is a vertical tangent. And besides all these cases, there is another situation in which a function may fail to be differentiable at a point if the function is not continuous at that point. The point is a point of discontinuity. In other words, differentiability has continuity as a necessary condition. If a function is differentiable at a point, it also necessarily has to be continuous at that point. Saying it differently, if a function fails to be continuous at a point, then it also won't be differentiable at that point. And let us see two cases of this. One of them is the function having a jump discontinuity, if you remember these things, at a point. Say this is the graph of our function which is in two pieces. It's broken at the point x naught. At x naught, its value is f of x naught. Note carefully that we have made this circle black and that one white. This means that at x naught, this is not the value of the function, but this one is. So the point here is p. Again, I cannot write it here, but let me write it above all these things. Okay. The white circle, we already know these things, but again I am repeating. The white circle prevents this curve from reaching the point, this point, because that's not the value of the function at x naught. This is the value. Now if we run our process in this case, say I take a point q to the left of me, it has to be on the curve, okay. So it has to lie on this segment. The secants, however, would pass through P and Q as usual. So you see a very peculiar thing here. From this side, the secants will, yes, they will approach something. They will approach a line, and what line will that be? That will of course be the vertical line that passes through x naught and p, and also passes through this point, which is not a point on the curve, not a point on the graph. So the slopes of these secant lines to the left of p, all these slopes are what? Positive, and they are becoming, these lines are becoming more and more vertical, which means that these slopes are approaching plus infinity. Okay, so the left hand derivative of the function at x naught does not exist actually, because the value is plus infinity. Whereas if you run your process on the right hand side, here the secants also assume a limiting position This line, however, is not vertical. This line has a slope, and this slope is a real number. So that is the right hand derivative of the function at p, and these two values are different, so the function fails to be differentiable at this point. And there is another case. Here we have a jump discontinuity where the values suddenly jump from this to this at x naught. But besides jump discontinuities, we also have removable discontinuities. What about that? Say you have a graph which goes like this, and at this point the function has this value, not that value. Okay, so this is our p, and this is our x naught. So let's take points Q minus on this side and draw the secant line as you move Q towards P. Towards P means here it doesn't really feel like towards P, but as close to P as you get, with the restriction that Q has to always lie on this curve. That is also almost the case here. I mean, this Q is going towards P, but it won't really go very close to P. On that side, however, it really goes close to P, as close as you want. Here, however, on either side of P, Q cannot really manage to go very close to P, but we just keep moving Q. And in doing so, these secant lines are going to eventually assume what? This vertical position. If you do that from the other side, there also, from that side also, the secant lines as you move Q towards P are going to assume that same vertical position as the line becomes steeper and steeper. However, there is a difference. For these lines, all the slopes are positive. So, the limit of these slopes is plus infinity. Whereas for these lines, all the slopes are negative. So, the limit of these slopes is minus infinity. So, unlike that case where the left hand derivative did not exist, but the right hand one did exist, here none of the one-sided derivatives exist. One of them is minus infinity, one of them is plus infinity. But anyway, the function here also is not differentiable. Now, this observation that continuity is a necessary condition for differentiability is in fact proved next. We are, however, not going to do that tonight. So, that is the next thing. And after that, there are some results which help us do many things about differentiable functions on intervals. So, we will see that in the next calculus update. So, that's just it for tonight. So, see you in the next upload. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.